This will be made available today. So you can watch, you can check on my YouTube channel. So we want to go into principal component analysis, and I'm going to be guided by this outline. I'm going to talk about the overview of that, talk about the data structure, the covariance, the correlation, orthogonal rotations, and so on like that. Okay, so let's get started. Let's look at the background. What is the purpose of principal component analysis? You know, you're going to benefit from the knowledge acquired in the study of linear combination. You remember before now, we focus on linear combination. Okay, so the principal component analysis, we find the linear combinations of variable that can explain the covariation structure of the variables. We want to believe that variation exists among variables. Can we have a way to explain this variation with few numbers of variables? Like we don't want to use all of them. And that is why it performed these two roles, data reduction. You know, instead of me to use p numbers of features, p numbers of variables, can I have a way to use R, numbers of variables, where R is less than p? Can we explain the variation using fewer numbers of variables? In that situation, we want to have what we call, that's why it is called, dimensionality reduction technique. And not only that, I want my model to be interpretable. And I need to be able to find features, okay, that are very, very important in explaining the variation that exists among variables. So when I say I want to figure out important features, then it means we're actually not going to use all the components. We're going to use those ones that can explain the largest variation in the variables. So these are typical purposes of PCA, the data reduction and data interpretation. But the whole thing is going to start from data matrix anyway. We normally start from data matrix. Okay, we have data matrix. Okay, in rows and column, we collected our observations and across several variables. Don't forget the subject. We represent the row. Y the column, the variables under investigation. And for the data structure, since the numbers of variables is more than one, we're actually going to have a covariance structure. Okay, this is a population covariance structure. The diagonal is going to be variances, like sigma 11 will be the variance of variable x1. Sigma 22 will be the variance of variable x2. So the diagonal element will be the variance of each variable, which I call the variation within. Okay, y the off diagonal will be covariances, so that will be covariance, the covariation, which is variation between. And of course, if I want to figure out the population variance, the sigma jj is expected value of xj minus mu j all squared. Then the covariance is that, and the mean is that. But this is not for sample. This is for population. I just wanted to take note. That was why we're using expectation. Expectation will take us back to the population. Now, because we're going to be working with data set, okay, because we're going to be working with data set, before I move on, can somebody online confirm if you can hear me clearly? The person online. I can see somebody online.
I can hear you.
Okay, thank you so much for confirming that. Okay, so because I'm actually going to have, data set, sample of data set, what I'm going to end up is going to be sample covariance. Now, when you take a look at this, whenever you see S like this, an uppercase S, without any subscript, that's a sample covariance. So, which means the elements of in this sample covariance, we're going to be dividing, we're using the formula that will be divided by n minus 1. But if you see this, can you see that? That would be MLE covariance. The MLE covariance is different from sample covariance. Okay? The MLE covariance is going to be the 1 divided by n instead of n minus 1. We've done all of this before because in the principal components analysis, we talk about explaining the covariations among variables. Then it is very crucial to look into covariance structure. That's why we're doing all of this. Now, in matrix form, this is how to compute the sample covariance. You need a deviation. Okay, SC, actually the deviation, then the transpose of that multiplied by that divided by n minus 1. That is how to get that in matrix form. Okay, just we've done all of this before. And of course, this is the SC itself. In case you want to know how to figure out the SC. Okay, now let's talk about correlation. Now, this is going to be population correlation. Of course, in this course, I think I've been able to distinguish between covariance and correlation. This is a population correlation, okay, matrix. Of course, the diagonal element is going to be 1, 1, 1. And of course, if you want to figure out how the elements within this correlation structure, that is the formula we talk about it earlier in the semester. Now, because we're going to be working with data set, then we need a sample correlation matrix. Okay, so we play a lot with notation. I really want you to see when I was talking about population correlation matrix, I was actually using P. Can you see that? P equal to that. But when it comes to the sample one, I'm using R. Please pay attention to all of that. So we're going to be focusing on the R or on the sample one because what we have at our disposal is sample data. We got sample data in our disposal. Of course, I'll walk you through how to get a correlation. In matrix form, of course, is the SSS is going to be the standardized one. When you want to get the one for the covariance, we use the deviation one. But to get the correlation in matrix form, the SS, this guy here is the standardized. Okay, the standardized one, and take a look at that. Okay, the standardized one is when you divide the element in the deviation matrix by its standard deviation, and that becomes a standardized one. And the moment I got that and I multiplied, I get the transpose and I multiply the transpose of that with that, I divide by n minus 1. That's going to give me the correlation matrix. I think we've done this before. Now, let me tell you this. Covariance matrix and correlation matrix, they're actually going to serve as an input matrix in principal component analysis. And that's why we're having a recap on them. Okay, now I want you to take a look at what make it possible to actually what make it possible for us to have data reduction by means of principal component analysis. We are actually looking for a way to project so many variables, maybe in 2D or 3D at most. Okay, We're able to do that because of the fact that we want to benefit from rotating points. Okay, rotating point. How can we rotate in such a way that the covariance structure is not going to change? Okay, mathematically speaking, okay, if I have a variable x and y, it's in two-dimensional space, and I want to do a 2 by 2 orthogonal rotation of x and y, okay, I want to demonstrate to you that, doing that rotation, the covariance structure, because this is what happened. We want to go from set of features to another set of features. Another set of features, the new set of features is going to be a linear combination of the old features, and we want to do it in a way that the covariance structure of the new feature and the old feature, they're going to be the same. We want to achieve that by way of rotation. In mathematics, it means if I have x and y, and I want to have a new set of variable. A new set of variable s star y star, and if I want to rotate, take a look at that. I'm rotating now. Actually want to rotate this guy to be able to get this guy, and there's actually going to be angle or theta for the rotation, and that's why you are having a trigonometric. Okay, now that is what we're going to use for the rotation. Okay, we can go counterclockwise. We can actually go clockwise as well. Okay, so if you take a look at what I have here now, this is a rotating counterclockwise, and this is for rotating clockwise. You can see this is cos theta minus sine theta, but here it is cos theta sine theta. Take a look at that. Now, how do we know that? And this is the visual, or visualizing the 2D rotation. No rotation, you can see the way what we're going to have with 30-degree rotation. So whenever you are talking about rotation, there will be angles that will be involved, the angle of rotations. And that's why you're seeing all of this. Okay? So take a look at that. When you have 60, when you have 90, and so on like that. This is the code, for that. But let me tell you this. Before we can preserve, the covariance structure, okay, during rotation, then we have a mathematical way to investigate whether that is being preserved, whether the covariance structure is being preserved. Now, take a look at this. If this is R, right, and I do the transpose, okay, this is R. The transpose of R is this guy, and I multiply R with the transpose, okay, it needs to be orthogonal for the formation to be preserved. What I mean by being orthogonal is that it should give me identity. The moment I have identity matrix, then it actually implies that the rotation that I'm actually going to do is not going to bring about change in the covariance structure. Does that make sense to everyone? And that's exactly what we've done here. Okay, because we need to investigate this mathematically to be able to see whether it gives identity. Now I'm going to move right now. We can do orthogonal rotation in I dimension too. I'll show you the way we do it 2 dimension. Okay, you can do it in I dimension. But let me tell you this. If I have a P by P orthogonal rotation, of course 2 by 2, 3 by 3, 4 by 4, it's going to be a square matrix. It's an orthogonal of linear transformation if the following hold. Okay, if the transpose of R multiplied by R is the same thing as this and is identity matrix, then it's an orthogonal rotation. Then, do you know, I need you to take a look at this. If X star equal to SR, don't forget, what do I want to rotate? I want to rotate X into S star using R rotation, right? Now, you're going to see something now. If this guy equal to this guy, can we prove that this equal to this? How are we going to prove that? Okay, this is how we're going to prove that. Okay, and I need you to pay attention. Now, if I have X star and the transpose of X star, the transpose of A, then it's going to be equal. What is X star? X star is given to be XR here, right? XR, then XR transpose, right? What is going to happen? I'm going to have SR, right? Then I'm going to have, when I find the transpose of that, it's going to be R transpose, S transpose, right? And this guy is an identity. Okay, so what I'm going to have is going to be X identity and S prime, which is the same thing as this guy, because identity, which is the same thing as that guy. That's what we just proved. Okay, that's exactly. Is there any question about how I go about this guy? Is there any question on that? All this is necessary. Okay, orthogonal rotation is a requirement. Okay, for this. Okay, now I'm actually gonna move right now. So, like I said, this is being recorded. Okay, that's being recorded. Now I'm gonna move right now. Now, I'll quickly walk you through population principal component. I'm also gonna walk you through the sample. Okay. The population is when you have a population of data. We don't normally have population of data. We normally take a sample. But let me show you this. Now, with principal component analysis, we want to have a set of, we want to have a linear combination of the variables that we have. From the linear combination, we want to produce a new set of variables. And that new set of variables, they're going to be orthogonal, they're going to be independent, and of course, we're going to use few of them. Now, please pay attention. I want to explain linear combination of random variables because that is what principal combination, principal component analysis actually, um, hide under. Okay, I have set of variables S1 or to XP, and this set of variables as there exists a covariance structure. Okay, now the eigenvalues of this covariance structure, okay, are the lambda 1, lambda 2 up to lambda p. Now you can see the lambda 1 here is actually telling us the principal components. The first principal component, we have the highest contribution, okay, followed by the second principal component and so on like that. And they have to be positive, okay? Now let us see the way the principal component analysis work. I have x1, x2 up to xn. This is the linear combination, the first one, the y1. The y1 here is PC1, okay? The y1 is going to be principal component 1. The y2 is a principal component 2. Okay, now you're going to see but we know all the way to principal component p. Okay, but you know what, if I have p numbers of features, okay, I don't want to use p numbers of principal component. I want to use fewer number of principal component, the one that can explain the largest variation. Okay, now you're actually going to see that the B1, the B11, the B21, the base, they are the parameters, they are actually the loadings. We call them loadings, that we explain how some set of variables load on to the PC. Okay, how they load onto the PC. So that's why I call them loadings. Okay, so now this is the typical model structure for the principal component analysis. Now, I want to move right now. If you take a look at what I have here, this is a particular principal component. Don't forget the X is a matrix. BK is also a matrix. I needed to pay attention to this guy here. You see that here or here, Here I use, this is in a scalar form, this is in a matrix form. Can you see that? This is in a scalar form, this is in a matrix form. Now, if I now want to focus on a particular linear combination, which means I want to focus on the particular principal component, it's actually this guy. Please pay attention. This guy, that's a K, it's principal component. Anyone? Maybe PC1, which is K equal to 1. I have a PC1, K equal to 2, I have a PC2. Now, the variance of a particular principal component is this. What do you think we're benefiting from? You remember we're benefiting from linear combination. You remember we did a linear combination the other time. This is the variance of the linear combination. Okay. Now, which is going to be the variance of a particular principal component. If I have two different principal components, YK and YL, the covariance is this. The covariance is going to be this guy. Okay, if you check what we've done before under the matrix algebra of linear combination, we've done all of this. Okay, now we're applying that now to principal component analysis. Now, we know we're actually going to be seeking what would be the parameter value, the B1, the parameter, values that we enable us to have the maximum variance. Now I need you to pay attention. I want to talk about the principal component now. I just walk you through the principal component and linear combination. And let me tell you this. Even if the original features are correlated, the principal component will be uncorrelated. And let me tell you this, in linear regression, there's this assumption that we call multicollinearity. Like, it's a problem. Multicollinearity is a problem with multiple linear regression where explanative variables correlate. The principal component can do the job of converting the correlated variables to uncorrelated one. So, but let me tell you this. What I'm going to do, I'm seeking to get the variance of the first principal component, okay, and I want to maximize the variance of the first principal component. What would be the values of the parameter that will enable me to do so? That is what that guy is talking about. So B1 is actually now, will be the maximum value, okay, that we actually are talking about. Now we have a B1. For the B2, because B1 has already exists, the first principal component has already exists. Under B2 condition, I have to, note that the covariance between the first and the second has to be 0. That is part of the restriction. Okay, because here we are trying to, we want to get the principal components that are uncorrelated linear combination whose variances are as large as possible, and that actually continue. Okay, that continue here. The maximum variance is what we're seeking. Okay, now moving on. This is visualizing it for bivariate case, the Y1 and the Y2. So you can see the Y1 here, this is the transpose of the eigenvector on S, the transpose of the eigenvector and an S. So take a look at that. And this is the angle I was talking about the other time. And this is I'm considering a situation where the mean equal to 0 and the correlation exists. Okay, we've done that before. Now, let's take a look at how principal component analysis work via eigenvalue decomposition. Of course, we're going to start with covariance structure of data set using eigenvalue decomposition. We can factor that. You remember we did matrix factorization, right? Matrix decomposition. So we want to decompose, what are we doing here? We're seeking solution for PCA. right? Via eigenvalue decomposition, and we're going to we're going to decompose the covariance into three components, okay, where V is going to contain the eigenvectors, and the one in the middle will be the diagonal one, and of course, we are going to have the transpose of the eigenvector. Please pay attention, okay? So you can see now, this guy is being partitioned into three. This is in matrix form. This is in scalar form. Now, what solution are we seeking? We believe that the variance of a particular principal component, when you do all of that, is going to be a lambda k, which means the variance of the first principal component will be lambda 1, the variance of the second principal component will be lambda 2, and so on like that. So what you see us doing, oh my God, what we're actually doing, take a look at this. This is yk, and yk is v prime x. Okay, what is the variance? This is a linear combination here. What is the variance? Then you're actually going to see that this guy is a constant. Coming out is going to be transpose here and here, and the variance of S is going to be the covariance. Can you see what we have? And right now, what are we doing? Okay, at this junction now, okay, don't forget, I said the other time, this guy is decomposing to three, right? Into that, that's what I'm bringing in. Okay, when I bring that guy in now, okay, simplifying, when you're trying to simplify that, that will give you the eigenvalue, okay? And the correlation between the principal, two different principal components should be expected to be zero because they have to be uncorrelated. That's what I mean, okay? Situation where the two principal components are not the same. Now, when I have principal components in place, how am I going to know the number of the principal component that is going to do a great job? Of course, because I'm looking for those ones, because I don't want to use all of them, but I actually want to select those ones that will explain the largest covariance structure, the largest variation. You know what? That's what called variance explained by principal component. Okay, now let me tell you this. Take a look at this statement. It's crucial. X1 up to XP, they are the original features. Y1 up to YP are the transformed features, the new variable, set of variables that we call principal component. And don't forget, each of them is a linear combination of the features, of the old features. They must have the same total variance as that. You remember when I was talking about rotation the other time? We want to rotate in a way that the covariance structure is not going to change. That's exactly what we mean. And that's what we're trying to say here. That's exactly what we're trying to say here. Okay, so the summation of the variance of x1 up to xp should be the same as the trace. What do I mean by a trace of covariance? Addition of the element in the diagonal of the covariance matrix. That's what I mean. And don't forget, by matrix decomposition, we said this guy can be decomposed into that, right? Okay, so don't forget that. And this guy here is the same thing as the trace of that. The trace of when you take a look at that guy, that's a diagonal matrix that contains the eigenvalues, and it's also going to be equal to the variance of y. Now you can see the variance of the old features, the total variance of the old features equal to the total variance of the new features that we call the principal component. Now I'm actually going to move right now. For instance, how do I, determine the percentage of variation explained by a particular principal component? Okay, don't forget, lambda k is the variance of a particular principal component, but what you have in the denominator is the total variance of all the principal components. Okay, so now if I do the ratio, of the variance of a particular principal component to the total variance, then I'm actually going to get the proportion of the total variance explained by that particular principal component. Okay? So that's exactly how what we can do. Okay, now I'm actually, but like I said, if I have P numbers of features, I want to use a principal, the number of principal component has to be less than P. Okay, we don't want to lose, we know that we're gonna lose information, but we do not lose much information. Don't forget, when you are transforming, transformation we actually come with lots of information, but we actually want to retain a principal component that we explained in the large. It's just like I have an image, and because of the fact that that very image has a lot of pixels and have a problem with data storage, how can I compress the image in such a way that I'm not going to lose the total quality of the image? That's what we want to do here. That's an example. Okay. Now we know there's going to be lots of information, but we don't want it to be we don't want to have a drastic loss of information that that will lose the total quality of the image. Okay. Now that is that. Then this is the covariance. Okay, like I said, the covariance, like for instance, you may want to do the covariance between the old feature and the new feature. Old feature is X, new feature is Y. We can also have covariance that exists between them because you have to you want to here we don't expect it to be zero. Okay, if you want to justify to the world, you know what is zero? You know the covariance that is zero. Covariance between any two principal components is zero, the new variables. But covariance between the old one and the new one must not be zero. If they are correlating, then it's sending an information that you've done a very great job. Now that is the covariance here. Okay, the covariance between the old features and the new features. And if you can see here, this guy is this guy, right? Okay, don't forget, principal component is a function of x, right? And this x is this guy here. Okay, just wanted to see that. Now I'm actually gonna move right now. This is, of course, you know that is the formula. Now you know what we've done all this while. We'll be focusing on population. Okay, I'll quickly run towards. I'll quickly walk you through the sample one. Okay, it's still going to be everything that we've talked about, except we're talking about sample. Okay, or everything that we've talked about. Okay, everything that we talk about. Okay, you can see instead of using the covariance or the one for the population, we're now using the sample one. Okay, and on the V, that was why you see a cap. When you see a cap, it means we're working with a sample, we're estimating. Okay, okay. So I walk you through this the other time. The proportion of variance explained by a particular principal component. This is the sample one. Okay. Now, and this is the sample covariance between the old feature and the new feature. Like I said, it has to exist. Now I'm going to move right now. Let's talk about large sample properties. When you have large sample, asymptotic. Okay. You know, why do we need this large sample property? We may want to test hypothesis or construct confidence interval on the eigenvalues. How significant is the variance of the principal component? If I want to know how significant, okay, take a look at this. When the features follow normal distribution and we're able to have eigenvalues, which has the variances of the principal component, as n tend to infinity, okay, this guy, do you see this guy? This guy actually means the estimate of the eigenvalue minus the mean divided by 1 over square root of n. This is a test statistic. For instance, I may want to test hypothesis about eigenvalue, a particular variance of the principal component when the sample size is large. Okay, what we are trying to tell the world is that the mean here will be 0 and the variance is 2 dash squared, the lambda squared. Okay, now what of if I may also be interested in the eigenvalue, eigenvector, okay, the distribution of that of the eigenvector. Okay, that of the eigenvector, the difference between the mean or between the estimator and the mean of the eigenvector follow normal distribution with the mean of 0, and this has the variance. Okay, and assumption here is that my eigenvector and my my eigenvalue and my eigenvectors are independent. Okay, they are independent, and that's why you see them distributing independently. Okay, now, oh, 1 second. I think I'm gonna share that again for you to see. Okay, now, so in case I want to test hypothesis, you know, about eigenvalue and eigenvector, that's why, and the sample size is large, that's why the distribution is very important. Now, can we talk about principal component analysis in practice now? I've walked it through. Now I walk it through eigenvalue decomposition. We can also do that. We can seek the solution of principal component through the singular value decomposition. So you remember the other time we did singular value decomposition under matrix factorization, where the XVD, okay, this is going to be that. You remember we have the UDV stuff. We can also use the idea, when we're seeking solution for the principal component. Okay, now in that regard, you can see my Y equal to that, my B equal to that, but the combination, this guy and that guy, of course, is this guy here, which is the singular value decomposition of X. Okay, the singular value decomposition of X. So I will advise that you can read what we've done before on that. And of course, here, the sample covariance is that. Okay, the sample covariance is that. And don't forget, the covariance is the one that we partition into 3 under the eigenvalue decomposition, where the first one is the eigenvector, the one in the middle is the diagonal matrix that contain the eigenvalues, and of course the one to the right is the transpose of that. Okay, so that's what we're using now. Okay, because of my time, I think I've explained all of that. Now let me tell you this. When you are working with principal component analysis, the input is either covariance matrix or correlation matrix. When do we use covariance matrix? When do we use covariance matrix if all the features, they have the same unit or they have the same scale. But if they don't have the same unit and the same scale and you use covariance matrix, then one feature will dominate the other. And the best input matrix to use should be correlation matrix. Does that make sense? Okay, like I said, PCA is trying to explain the variation in S in covariance structure or in correlation structure. Okay, so and that's what I'm trying to say here. They are appropriate for use. Look at this. If the units of P of variables are comparable, then covariance PCA may be more appropriate. But situation where they are incomparable, if they are in a different unit or they are not in the same scale, then we have to use a standardized covariance. Standardized covariance is correlation matrix. Okay. Uh, I think it's best time we go into example. Let's take a look at example. And I want example to come from men's Olympic decathlon data from 1988. We have 34 athletes and we have 10 variables. Okay. And these athletes have participated in 10 different events. I said that's what I mean by decathlon, decathlon in Olympic. Okay. Athlete participating in, and these are the events. This is the data structure. Okay. The same athletes, these are the names of the athletes. Oh my God. Take a look at the names of the athletes. Each of them participates in 100 meter, the long jump, and so on like that. And this is their score. And finally, this is the score. Okay. This is the score across all events. Has anybody seen an athlete doing this before in Olympic, or where he's going to do or run 100 meter, he's going to do long jump, he's going to do all the events. At the end of the day, they're going to score them. Even though we have some athletes that specialize in this event, but we have some athletes that do all of these. Okay. Now we got a lot of features here, and we believe the idea we can use a principal component or to prune down the numbers of variables. Now, let me tell you this. You know, if you look at all the events together, please pay attention. If you take a look at all the events together, it's a combination of running events and field event. The running event, the best time is when you have a low time, right? But in the field event is the other way around. You understand what I mean? So what we're going to do is we realize that we need to transform this data set. And that is exactly what I'm trying to say here. Pay attention. I said for the running events, those one, lower scores correspond to better performance, whereas higher score represent better performance in other events. Because of that, something need to be done to my data. Okay, what do I need to do to my data? Look at what I'm doing here. Please pay attention. 1, 5. Okay, 1, 5, 6, 10. Okay, this is 1, 2, 3, 4, 5. Okay, 6, 7, 8, 9, 10. What are the one that I'm multiplying by -1? I'm multiplying the running events by -1 so that they are going to be on the same level. Does that make sense? Okay. That was exactly what I'm actually doing here, where you see -1 multiplied by column 1, 5, 6, 10 corresponding to the running event. Okay. Now, how do we do this now? If you want to start with, I'm going to do both covariance and uh, correlation. Okay, this is loading the data setting out. Okay, and this is getting the PCA. I mean, getting the covariance. The covariance is such, of course, is COV. So if I want to construct the principal component, take a look at this. Okay, principal component around the data, or the variable 1 to 10. Okay, that's exactly what I'm doing. And this is the PCA solution, the code. Okay, and at the end of the day, I'm actually going to get the structure. Now take a look at this. This one here is for the correlation one. Okay, you can see core. Okay, and what is the difference? Take a look at here. Core equal to true. If I don't put anything there, then it's going to assume for the covariance. Okay, so take a look at the code. Okay, now study the code. Then I'm going to come here now. Let me just come here. This is the principal component analysis for PC1 and PC2 loadings. Okay, and for the correlation matrix. Now, let me tell you this. If you look at the PCA, if you look at the covariance matrix here, you're actually going to see javelin, discus, and shot put. Okay. Now all they are actually clustered together. When they are clustered together, means that the angle of rotation between them is very close to zero. Because of that, I'm actually going to say they are positive. They have positive loadings on PC2. Okay, they are positively related. Okay, when you take a look at what I'm having here. Okay, now there's something I want you to understand. When the angle is very small and it is zero between variables, it suggests a strong positive relationship. When the angle is 180 degree, that's a negative relationship. When the angle is very close to 90 degree, 90 degree actually means, there's little or no correlation among the variables. So I needed to pay attention to all of that. Now I'm actually going to move right now. So I think I provided a code. You can study that. But you know what I'm doing now? The other time I was trying to show you covariance must exist between the old score, between the old feature and the new feature. What is the old score here? Is the Catalan score. Can I see, is there a relationship between PC2 score and the Catalan score? This is kind of spread out. This is saying that there's little or no correlation between the Decathlon score and the PC2 score. But when you come to the correlation, oh my God, the relationship is a straight line one. Can you see that? Between the Decathlon score and the PC1 score. Okay? That's what you can see there. Now, uh, I think I've talked about, now, the last thing we want to do before we go today is this. How do we decide on the number of principal component? Because I told you the other time, the number of principal component has to be less than the number of odd features. Okay, we use a script plot. Okay, we actually use a script plot for that. And this is a script plot. A script plot will show the plot of the variance against the component. Okay, now I needed to pay attention to this one. This is a script plot generated for the when we use covariance structure as input, and when we use correlation matrix as input. I needed to pay attention to this. Okay, pay attention in the covariance matrix. One, explain about 180. Principal component one, explain 180. Okay, okay. The principal component two, explain 50. The principal component three, explain 10. But when you look at from principal component 4, that flatten out, which make the variance to be negligible. Okay. So if I want to choose here, I'm going to say between 2 and 3 principal component. Does that make sense? Between 2 and 3. In fact, 2 will do the job. Can you see that? Now, when you take a look at in the correlation one, okay, when you look at the correlation one, okay, 1, explain 5, 2, explain that, and 3, explain that. And when you look at every, from 4, it flatten out because it doesn't have much variation. So, when taking a look at this very two now, by screen plot, by using EBO, I'm actually going to say, the number of principal components that we need is going to be 2. You know what we've done? Using 2 principal component now. Don't forget, each principal component that we arrive at, we still retain the old information because it's a linear combination of the old features, but we don't have the entire information intact. Some have been lost, but we are still able to retain with the principal component 1 and 2. We are still able to retain the most significant amount of information. Okay, and that's exactly what I need. Particularly, I want to go back into. I want to give more information on this one on this one here. Oh no, no, not that one. On this one here, and I need you to pay attention. I remember the other time I said when the angle between variables is small, okay? When the angle is very, very small between them, it implies a very strong positive correlation. When the angle is close to 180, it's negative, it suggests a strong negative correlation. When the angle is close to 90, okay, it means there's a little or no correlation whatsoever. So if you look at the PCA covariance, okay, if you look at the PCA, you can see, I think javelin, you see javelin, discus, and shot put. I needed to take a look at that. Okay, the angle that they have is very close to zero, and they cluster together. Because of that, they have high loadings, high positive loadings on PC2. That's what I mean. Okay, and that suggests they are positively correlated. Okay, with that. But I need you to pay attention to this guy here. Mm, look at that. That has a high positive loading on PC1. Can you see that? High positive loading on PC1. If you take a look at, that guy, okay, in the covariance matrix. And of course, if you want to talk about the correlation matrix as well, you actually going to see that run 1005, they run 400, and maybe this very too. Okay, they actually load high too. Okay, so I wanted to take note of that. They load high on PC2, and of course, if you want to see, let me see, uh, stuff like long jump. I take a long jump, the high jump, the pivot, and the auto. Incidentally, these are feed events, right? They are feed event. You can see they cluster around, right? If you take a look at that, they cluster together, okay? And they cluster together, they have a positive loading on PC1. So take a look at that. They have positive loading on PC1 means, you know what it means? Because when you have a PC1, when you have a PC2, you want to be able to see what are the variables that are more associated with PC1. What are the variables that are more associated with PC2? So when you write the equation out, you'll be able to see from the loading, okay? The variable that load more, okay, on a particular PC is highly related to that PC. Does that make sense? So we've been able to partition the set of variables into two. Some that load more on a particular PC will be known for that PC, and some that load more on the other PC. So as I'm saying here, you actually going to see all of this. They load more on PC1. Okay, they load more on PC1, and this guy here and this guy here load more on PC2. From what I'm seeing now, it's like PC2 represents track events in a way, while the PC1 represent the feed events. You see now, we've been able to project so many events into two-dimensional, into just PC1 and PC2. And that is a motive. This is where I'm going to stop today. The next topic will be factor analysis. I've already uploaded that material on the canvas. You can see that. Is there any question before I go today? Any question? Okay, it's gonna be another weekend from tomorrow. Make sure you all stay safe and have a lovely day. And of course, I think I'm gonna post from today. You're gonna see probably the solution to the midterm, and at the same time, um, tomorrow you go to see. I like you're gonna see the grading for the assignment 3. I think assignment 4 is on, right? Okay. Stay safe. Bye for now, everyone.